Okay, homework 4 is due on Tuesday next week, and then a week from today is when we'll have the first exam. I've already put a sample exam online, and there's the formula sheet available online, so you can kind of get a feel for like the typical style of an exam question. And I know some classes have the idea of lots of small questions. I lean more towards concepts or questions that are multi-part, and so you can expect to see 3 or 4 problems on the test. And we have a 75-minute class, and I take that into account when I write the exam, that you've got a limited amount of time, and I think that most people will finish the exam in less than an hour, but that all partly depends on how naturally quick you are at the material, but then also how well prepared you are, because if you're not well prepared, then no amount of time is going to feel like it was enough. So it's definitely not something that you can come in and figure out if you haven't been studying up till now, but it's also at the same time not anything that you need to be overly intimidated by, or cramming shouldn't be necessary if you've been keeping up with the assignments and reviewing the textbook and working through the examples during class. Today we're going to continue talking about hydrostatic forces on curved surfaces, and that was first introduced with the recorded lecture from Tuesday, and it was a pretty in-depth question on that Tuesday example. There's a lot of calculations into that, so we'll just take a moment to review the main ideas and then reinforce it with another calculation example that, since we're in person again today, you did the example on Tuesday in isolation with the video, and so I think it's important for us to do one together where you're able to collaborate and kind of think through the problem with your classmates on this next one that I'll give you today. We'll also begin talking in the lecture context about buoyancy, and that was the topic of the lab that you did on Tuesday. By raise of hands, did everybody get into the lab on Tuesday and do that experiment? Yeah, anybody have trouble getting in there? I don't think that the room was locked. I didn't hear anything. All right, so we'll talk about buoyancy a little bit more. Now, first though, I wanted to give you a couple of hints on the homework. And so this slide doesn't appear in your lecture notes, but you may want to just jot down a few ideas as we talk through it. Has anybody already looked at this problem in the assignment? One? Okay. So the basic idea here is that there's a tank of water, and there's a cone plugging a hole. And so just visualize now in 3 dimensions what a cone looks like. I guess I could hold up a little piece of paper, and if you fold it just the right way, you can make it cone shape. All right, so here's a cone shape, and it's plugged into a hole. Okay, so what this is asking is what force F is required to hold the cone in place. So the dimensions of the cone are provided. You see that it's 2.6 meters above the water line and 2.6 meters below the water line. And so that gives you the height of the cone. And then this angle can be used to find the volume of the cone. And the formula is in your book, and you can probably find it in other places as well. But with the volume of the cone and the given density, then you can find out what the weight of the cone is. In other words, you can find out how many newtons downward the weight force is that has to be supported with, like, I suppose it's a line going up to the water surface. And so that's part of it. But what's the other component besides the weight of the cone itself that this force is going to have to resist?
The hydrostatic force coming down vertically from the weight of the water, not only in the cylinder above the cone, but also the weird, like, sloped cup shape on
Okay.
top of the cone.
Right, right. So there's water in here, and the pressure is working to push the cone out. And so probably the easiest way to calculate the effect of the water acting downward on the cone is to find the weight of the water that's above the cone. And so what you have to do is you have to think about what kind of, in 3 dimensions, what's the shape of that element of water that's above the cone. And so I don't want to give too much away, but if you just kind of close your eyes and think about what's the inverse of a conical shape. So the cone is projecting into the water, so you need to find out the volume of water that's immediately above the cone. Now, to the side of the cone doesn't matter. So like how wide this tank is, that doesn't affect things one way or the other. It's just the weight of the water that's immediately above that portion of the cone that projects into the tank. So it doesn't matter how much of the cone is beneath the tank. It just matters how much of it is in the tank of the water, and then you need to find the weight of the water that's above it. And so F is going to be the sum of those two things, the weight of the cone itself plus the weight of the water that's above it. Okay, so I wanted to give you that hint. And then on problem 3, this is a hydrostatic force problem with a curved gate, and we're going to work through another example today. So you'll get some additional practice on this. And as was mentioned in the example on Tuesday, the 2 main things in a curved gate problem is the horizontal forces and the vertical forces. And the horizontal forces are equivalent to the force that would have acted on a projection of the curved gate. And so you need to think about, if a light was shining from the side, what would the vertical projection of that curved gate look like? And that'll tell you the horizontal forces. And then the vertical forces are related to the weight of the water that's above the gate. But here you can see that what's above the gate is just air. And so there's actually no weight of water above the gate. The vertical hydrostatic forces, instead of acting downward, the water is pushing up on this curved gate. And so the magnitude of the vertical hydrostatic force is equal to the weight of the water that would be above the gate if you continue this water line to the side. And so just imagine that there's some element of water above the gate, and that's going to be equal to the vertical hydrostatic force that the water itself is pushing on the gate. So it's just kind of an asterisk to the idea that the vertical hydrostatic forces are equal to the weight of the water above the gate. Here, there's no water above the gate. It's just air. And so the vertical hydrostatic force that's pushing up is equal to, essentially, the weight of the water that's been displaced by the gate. Because if the gate wasn't there, where would the water be? That's what you have to ask yourself, is how much water is this gate holding back? And if this gate wasn't there, the water level would rise to this same elevation that the water is on the right of this concrete piece. Okay. So if that doesn't make immediate sense to you right now, hopefully with the rest of the work that we'll be doing today, that will. Any quick questions on these 2 hints before we move on? All right. So this is the one we did last time in the recorded lecture on Tuesday. This is the shape. And the key to, as I just mentioned, the horizontal forces, so the force that's acting on the side of the gate, is you have to think about what is the vertical projection. And so in this case, the vertical projection had a height of 3 meters, because 3 meters was the distance from this centerpiece up to B. And so the horizontal forces are equal to the weight of the water that would act on the vertical projection, and then the vertical forces are equal to the weight of the water that's above the gate. And so we had to break that volume of water above the gate into equivalent pieces, into components. Okay, I just wanted to make sure I was recording. I didn't remember pressing the record button. All right, so the components. And so just think about that we have a rectangle, and then we've got a rectangle minus this quarter circle. And so that component that's left over was element C. And so when you have these curved gates, it often, as a first strategy, makes sense to think about breaking the volume of water above the gate into simpler components. And that's what I'm going to ask you to do in this example. I have a paper printed that I'm going to hand out. And the reason why I've printed it is so that you can sketch on the paper. And also we're going to do the thing where you scoot together with another student and kind of collaborate on it together. So let me hand these out. Okay, so scoot to another student right now. Nobody's sitting alone for this one. Right next to somebody else. And the first thing you need to do here at the top, break this volume into simply shaped components. And so think of the dimensions and try and sketch in 3D. Like a cube. What are the dimensions of the cube of water? What are the dimensions of the other shape that exists above the gate? So break it up into simply shaped components, and then we're going to go through the steps of the horizontal force, the location of the hydrostatic horizontal force, and then the magnitude of the vertical. But I have not asked for the location of the vertical. We did that in the example on Tuesday, but today let's just find the magnitude of the vertical hydrostatic force. Okay, let's pause for a moment and just take a look at the horizontal part of it so far. If you haven't yet completed the vertical, that's okay. I'll turn the time back over to you for that. But let's just make sure we're on the same page with the horizontal. So over on the whiteboard, I've sketched what the vertical projection would look like. And so that is, if you're looking at that curved gate from the side view, what are the dimensions of the gate? So from the side, it's going to look like a gate that's 4 meters wide, because it mentions in the problem statement that distance into the page that we can't see from this side view is 4 meters wide. And then the height of the gate would be 2 meters. So it's going to be this radial distance from the bottom up to the top. So what our challenge is for part A, where we're finding the horizontal magnitude, is to take into account the vertical projection of the curved surface. So here you can see that I've designated the height of 2 meters as component B that later on we're going to use in the area moment of inertia formula, and then the width of the gate, 4 meters, is A. Now also up here at the top, I've taken into consideration the given density of this liquid. And so the liquid density is 0.745 kilograms per liter. And if we want to know how many kilograms per cubic meter, then we multiply that by 1,000, since there's 1,000 liters in a cubic meter. So that's what I've done in this first conversion here, is I've just said 0.745 kilograms per liter is 745 kilograms per cubic meter. And then if we multiply that by G, it's how we get the unit weight of 7,308 newtons per cubic meter. All right, so the horizontal magnitude is easy because the vertical projection of a curved surface is a vertically oriented component. So it's relatively straightforward for us to find, for example, the depth to the centroid. Just by inspection, we can see that it's the distance 3.7 meters, which is the distance from the water surface down to the top edge, and then 1 more meter to get to the center of area of the projection. And that's the tricky thing, is we continually have to keep in mind what the projection looks like. So the delta H is 4.7 meters. Multiply that by the unit weight, and then the area of the gate projection is 8 square meters. It's not the actual physical area of the gate, but the area of its projection. So the horizontal force should be 274.8 kilonewtons. All right, did anybody else get that same value for the horizontal force magnitude? Okay, good. Now its location is going to be below the center of area. And so the centroid that we just found for this hydrostatic force magnitude, remember that YCP distance is going to be a little bit more than Y bar. And here, because it's vertically oriented, Y bar equals delta H. So, in one sense, these curved gate problems are a little bit easy because the horizontal forces are a vertically oriented projection. So Y bar is equal to delta H, and that's 4.7 meters. You can calculate the area moment of inertia, and it's a rectangular shape. So we find 2.667 meters to the fourth. And then YCP we can calculate with Y bar plus I divided by Y bar A. So 4.771 meters is the distance, the vertical distance from the water surface to where that force is applied to the gate. Now remember, there isn't really just a single force acting on the gate. What really is happening is that there's a distributed pressure acting over the entire area of the gate. But for other types of analyses, like if we wanted to know what kind of force had to be supported at the junction of the curved gate and the frame that it sits in, it's okay for us to just calculate this equivalent point force of the hydrostatic pressure that's acting over the entire area. So that's kind of why we are saying that there's this one force that has 274.8 kilonewtons and it acts at this single location. It's essentially the equivalent force and location. All right, so that's the horizontal component. Now, the vertical component of it, you can sort of get a sense for how I've divided up the volume that's above the gate. The first thing I suggested you do is break this shape up into pieces. And so here, piece 1, I'm calling a rectangular cube that has a height of 3.7 meters, a width of 2 meters, and then a depth of 4 meters. So that's going to be the volume of element 1. And then element 2 we find by subtraction, because there's another rectangle, and if you subtract out the quarter circle, then that piece that's left over is component 2. All right, so I'm going to pause again, give you some time to finish up finding the weight of the water, because that's the essence of this last part. The magnitude of the vertical hydrostatic force is how heavy is the water above the gate, immediately above the gate, not to the side of it, but just the water that's immediately above that curved gate. If you find its weight, then that's the force acting downward. Okay, so let's take a look at what are the two volumes that are above that gate. I've labeled them as element 1 and element 2. So element 1 is rectangular in shape. Element 2 is like this leftover after we extract out a quarter circle. So element 1 is relatively easy to calculate the volume of that. It's just 2 by 3.7 by 4. So it has a volume of 29.6 cubic meters, and then we can find the weight of the liquid by multiplying that volume by gamma. So element 1 has a weight of 216 kilonewtons. Element 2 is a little bit more complicated because what we do is we, first of all, calculate the overall volume of a rectangle that's 2 by 2 by 4. So it's 2 in width, 2 in height, and 4 in depth. And then we subtract out the quarter circle. So the quarter circle, pi r squared divided by 4, is the area of that, and then you can see that I've multiplied it by 4 to give it its depth into the page. And so the volume of element 2 is the 16 cubic meters of the overall rectangular volume, and then the quarter circle volume that's been extracted out is 12.5 cubic meters. So what's left over is 3.43 cubic meters, and from that we can find the weight of element 2 and the overall weight that's vertically acting down, 241 kilonewtons. It varies, but this is pretty regularly on the first exam, a question like this where you find the forces on a curved gate. There's as much chance that you'll see one of these on the test as anything else. Okay. Well, let's move on to a discussion of buoyancy now. And buoyancy sometimes pops up, pun intended, in unexpected places where this is a photo from a few years back. I believe it was a picture taken in Charleston. And you can see it's at a gas station that appears to be closed, like it's no longer being used. I just want to make sure I've got that recording going. Yeah, all right. So we've got an abandoned gas station that has an underground storage tank they use for the fuel. And you can see that this is kind of an unexpected thing. They've got this emergency yellow police tape around the edge of it. And it appears that the fuel tank has broken through the concrete that's at the surface. And so it's a very unusual situation where what happens is that during rainy weather, the soil that this tank is buried in becomes saturated with water. And that water that's in the soil exerts a buoyant force on the tank. And if the tank is laden with fuel and is really heavy, then nothing will happen. It'll stay underground. But it's this rare case where, with really rainy weather, the water table went up, and this filling station no longer being used, the fuel tank was empty, so that it didn't have much weight. And so the buoyant forces exceeded the weight, the downward forces, and it caused essentially this tank to float, even though what we usually think of floating is, in open water. It can also happen in saturated soils. So this is kind of an interesting fringe situation that illustrates that buoyant forces sometimes apply even in circumstances that you wouldn't expect. Let's watch a video that kind of illustrates a more typical situation that we think of buoyant forces. All right, let me pause this. The equilibrium is taking into account the weight of the object and the external buoyant forces that are acting on the object. And so if it's still rising, what does that tell you about the balance of forces between weight and buoyancy?
There's more buoyant force pushing it up.
That's right. There's more buoyant force pushing it up if it's still in the process of rising. So let me just take it back a couple of frames. Still rising, there must be an imbalance of forces. But then it comes to the surface and it doesn't keep floating. It's not floating into the atmosphere. But it comes into an equilibrium where right now its buoyant forces and its weight forces are equal. And so we'll talk about what allows us to calculate the magnitude of the buoyant forces, and then we'll come back to this specific example of the submarine a little bit later. All right, so generally speaking, this is applicable regardless of what the shape of the object is, that the pressure on the underside of an object is larger in magnitude than the pressure on the top of the object. And the reason why is that the object bottom is deeper. And since it's more deeply submerged, the pressure forces are higher. And so the size of the arrows here are meant to give you an idea just that the forces are greater on the bottom. Now this can be an irregularly shaped object, and that makes it a little bit more tricky for us to calculate the magnitude of the force at any particular location. And if it's irregularly shaped, then the pressure forces are going to be normal to the surface. And so here you can see that it's a little bit sideways and coming in from a different direction, but it turns out that there's going to be a much simpler approach than this first idea, that is just let's find the difference between the pressure forces from beneath and the pressure forces from above. So we have some submerged object, and what we could do was we could say what's the volume of the water above the object and what's the volume of the object itself, and then find the difference between them. So the forces that are acting upward are going to be equal to the weight of the water that is above the object, and then the weight of the water that the object displaces. Because this body is floating in this case, water, and so it's pushing water out of the way that would have been there if this object wasn't where it is. So it's displaced water. And so the upward buoyant forces are equal to the overall volume multiplied by the unit weight of whatever fluid is being displaced. The downward forces, so the pressure that's acting on the top and is pushing the object down, is simply related to the weight of the water that's above the object. And so the net buoyant force is the difference between the pressure forces from above and the pressure forces from beneath. And so it turns out that if you look at the two volumes that were in the upward forces, object B and volume A, and then you subtract out volume A, because those are the downward buoyant forces, all that's left over is the unit weight of whatever this liquid is multiplied by the volume of the object itself. So the generalized principle that we can apply to any submerged object is that the buoyant force is equal to the unit weight of the fluid multiplied by the volume that's displaced. And so whether this is going to float or sink depends on whether the buoyant force is greater than the weight of the object. And so like if this is a rock, like maybe quartz, really dense rock that has a greater density than water, then it would sink. But if this was made out of relatively lightweight wood, like pine, it would begin to float to the surface. And so what determines whether a submerged object floats or sinks is the density of the object compared to the density of the liquid that it's submerged in. Any questions so far? All right, so let's consider this submerged plastic cube. And what we could do is we could start by finding out the hydrostatic forces just due to the pressure at a depth. So you can see that this submerged cube, the top edge of it is 3 meters beneath the surface. And so the top force is going to be equal to, remember the definition of force is pressure times area. So force top is going to be the pressure at the top multiplied by the area of the top. Okay, so pressure is delta H times the unit weight of the fluid. In this case, it's water. So that gives us the pressure multiplied by the area of the top. So from the water surface down to the top of this cube, the delta H is 3 meters. The unit weight, since it's water this time, 9810 newtons per meter cubed. And then the area of the top, it's a 1 by 1 area, so 1 meter squared. Okay, so the force that's acting on the top, if we multiply those things together, it's 29,430 newtons. 29,430 newtons. And so that force is acting downward. So you could think of that as the weight of water that's above the top of the cube, or just the pressure acting over an area. It's one and the same. So that's the top force. The force on the bottom, similar idea. It's the pressure at the bottom multiplied by the area at the bottom of the cube. So it's going to be delta H times gamma times the area, but this time the delta H, instead of being 3 meters, because it's a 1 by 1 by 1 cube, the delta H is 4 meters. So 4 meters multiplied by 9810 newtons per meter cubed. And then the area is 1 by 1 again, because that's the area of the cube at the bottom. So the hydrostatic pressure that's pushing upward is going to be 39,240 newtons. And so the difference between the two, like the net force between this big force on the bottom and the relatively smaller force that's acting downward, the difference between the two, force bottom minus force top, is 9810 newtons. Let me just bring these calculations up onto the screen so that this one gets included as well. All right, so you can see that we calculated the force of the water acting upward on the bottom, the force of the water acting downward on the top, and then the difference between the two, 9810 newtons. Now, why is it this familiar, 9810? Well, it's because it has dimensions of 1 by 1 by 1. The other way that I suggested we consider this is, let's look at the difference, which we just did, and compare that to the buoyant force by just the unit weight of the fluid and the volume of displaced. So this cube displaces 1 cubic meter of water because the plastic is in a location that if the plastic wasn't there, it would be filled in by water. So the buoyant force is effectively just the unit weight multiplied by the volume that's been displaced by the object. So you could calculate it instead of having to compare the forces on the top versus the forces on the bottom. As long as you just know the volume of the cube or whatever the object is, if you find its object that's underneath the water level, then that's the buoyant force. So buoyant force, this is a generalized formula. Buoyant force is the unit weight of the fluid and then the volume of fluid that's displaced by the object. So if an object isn't fully submerged, the buoyant force depends just on the submerged volume. So it doesn't matter how much of it is above the water surface, it's just how much is beneath the water surface, and that's how you calculate the magnitude of the buoyant force. Does everybody understand the distinction between the submerged volume and the overall volume? Because the overall volume here extends above the water line, but it's just the submerged volume that's displacing water. Okay. We have another floating plastic block, but this time instead of being all the way under the water surface, this one is floating partly submerged. It tells us in the problem statement that the block's dimensions are 5 by 10 by 10. So you can see it's 10 meters wide, it's going to be 10 meters into the page, and then the height of the block is 5 meters, but it's only submerged 4.6 meters. And so some of it, 4/10 of a meter, is poking up above the water surface. Now, there's a lot that we can learn by how a submerged object floats. We can find out things like the specific gravity and the specific weight based on how an object floats in equilibrium. So here you can see I've asked some questions numbered 1 through 5, and they're asked in kind of a sequence that I think one leads to the other. So the first point here, what is the buoyant force? Use this equation. It's the volume displaced multiplied by the unit weight of the fluid. So here the fluid is water, unit weight 9810, and what I'd like you to do is, since it's floating in equilibrium, I'll tell you that right now, it's floating in equilibrium, that means the buoyant force is equal to the weight. So all the rest of these you can calculate knowing that it's floating in equilibrium. So let me pause for a second, give you a few moments to do these calculations. Okay, I've sketched out what the block looks like. 10 meters wide, 10 meters depth, and then it has an overall height of 5 meters, but it's only 4.6 meters from the water line down to the edge. And so how much water is being pushed out of the way by this floating block is 4.6 by 10 by 10. And so the overall buoyant force is 4.5 meganewtons. A relatively large block here. And the weight of the block is going to be equal to the buoyant force because we're told that it's floating in equilibrium. So buoyant force and weight are equal. So there's no separate formula for the weight of the block. It's just applying the concept that if it's floating in equilibrium, that the weight and the buoyant force are equal. The overall volume of the block is just 5 by 10 by 10, so it's 500 cubic meters. So that now if I want to know the specific weight of the block, if I want to know gamma of the block, it's going to be the weight divided by the volume. So 9025 newtons per meter cubed is the unit weight of this block. And then the specific gravity is simply that divided by the gamma for water. So 0.92. Now, it's not a coincidence, but it is kind of interesting that if you divide the submerged depth by the overall height of the block, it's also 0.92. So you just do that in your calculator right quick. What is 4.6 divided by 5? 0.92. So what that tells us is that the way that a submerged object floats in equilibrium is directly an indicator of its specific gravity and unit weight. So a similar example is like an iceberg. You've probably heard before that when an iceberg is floating, just the tiniest little piece is sticking up out of the water, and then the vast majority of the volume is beneath the water. And so how much of the volume is above the water versus beneath the water can give you an idea of the density and unit weight and specific gravity of the ice that the iceberg is made out of. So the reason why it floats is its density is less than the density of liquid water, because water expands when it freezes. All right, so that is our first taste of buoyancy, and let's take a look at a more complicated example here. Now I'm going to talk you through this one. The calculations are a little bit involved, and so I think based on the time that's available, we'll stick with my calculations, but I do want you to kind of mentally follow along and engage with what's happening here. We have a floating wooden block at the top, and so it has relatively low density, and that's why it's floating up above. Is component 1 is less dense than water. And then beneath the water, this object 2 is made out of metal. So it has a greater density of water, so it's sinking downward, but they're connected by a cable. And so the reason why object 2 doesn't just sink to the bottom of the tank is it's being suspended by the cable. And if that cable wasn't there, object 1 would probably float higher in the water than it is right now. So it's being dragged down a little bit more than it ordinarily would because of that added weight. So that's kind of the qualitative overview. If you look at the dimensions here, it says we have an overall height of 10 millimeters from top to bottom of that block, and elsewhere in the description it says it's 50 by 50. So that means the width is 50 millimeters, and then the distance into the page is 50 millimeters. It's described as having a specific gravity of 0.3. So with that specific gravity, we could calculate the density of the block or the unit weight of the block, which we would need in order to calculate the weight that's acting downward because of object 1. Another piece of the given information is the volume of the metal object. And kind of annoyingly here, the units are in cubic millimeters. So we have to be really cautious about converting cubic millimeters into cubic meters. So how many millimeters are there in a meter? How many millimeters? So if it's 1 meter, we know that it would have 100 centimeters and 1,000 millimeters. So 1,000 millimeters. Sometimes I see people accidentally saying, well, then that must mean that this is 6.6 cubic meters. But it's not. If it's 1,000 millimeters, that's just the 1D dimension conversion. If you want to convert from millimeters cubed into meters cubed, you have to cube this. So it's 1,000 millimeters by 1,000 meters by 1,000 millimeters. So how many millimeters cubed are in 1 cubic meter is 1,000 times 1,000 times 1,000. So you can do that now. Multiply it together. 10 to the 9th. All right. So the overall problem here, like what it's asking, step by step, we could use the way that this floats, the way the system floats, to calculate what mass object 2 has. And so what we would do is we would first calculate the buoyant forces, because we know the submerged volumes. So the buoyant force on object 1 and the buoyant force on object 2 is just related to the submerged volumes. And then the weight of object 1 we can get from the given specific gravity. So let's take a look at those first couple of steps. Okay, so here's our system. Object 1, object 2. So the buoyant forces are going to be related to the volume that's underneath the water surface. So how much water is being pushed out of the way by each of these. So object 1, I've converted its given dimensions that were specified in millimeters over to meters. So 0.0075 is the depth of submergence, and then the width and the height of the object multiplied by the unit weight. So we have a certain buoyant force of object 1, the buoyant force of object 2. We were given its volume and it's fully submerged. And here you can see the conversion factor that we were finding the volume of object 2 in cubic meters. So we know both of the buoyant forces, and now the weight of object 1. So what it initially gave us was a description of object 1's specific gravity and its overall volume. So the weight of the object doesn't depend just on the submerged volume, but the overall volume. So here you can see V1. I'm not talking about the volume displaced. I'm talking about the full volume beneath the water surface. So we can find the weight of object 1, and now a force balance on object 1 to find the tension in the cable. Now this is important. If we just isolate what's happening with object 1, there's the cable that's pulling down, there's the weight of object 1 that's acting down, and then the buoyant forces are pushing up. And those three forces together are in a static equilibrium in the vertical direction. So the buoyant force that's acting up is counterbalanced by the weight that's down, and the tension in the cable is also pulling down. So from that we can find the tension in the cable, and then doing a force balance with object 2, the tension in the cable is pulling up, the buoyant force is going up, and the weight is going down. So here the only unknown was the weight of object 2, because we knew the tension from the previous force balance, and the buoyant force acting upward on object 2 we calculated in the preliminary calculations, and so now we have the weight of object 2 by this force balance. And then the final thing, the mass, is simply going to be taking g into account. So the weight of the object divided by g tells us that we have 0.0179 kilograms. And so I would encourage you to think through this example and kind of the order of why things were asked one step at a time and how we can learn from buoyancy. that's all the time we have for today. Remember that the next homework assignment is due on Tuesday, and then the exam is on Thursday. So have a great day. I'll see you on Tuesday.